Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about real behavior of gases. You know my friend, this is very important topic from gases state. So let us start learning of behavior of real gases. You know the behavior of real gases is expressed mathematically by what is called the equation of a state. You know that. The equation of a state is an expression that gives the relations between pressure, volume, and temperature of a substance in any state of aggregation, not restricted to gas only. If any two of the quantities pressure, volume, and temperature are known, the third has fixed value dependent uniquely on the other two and can be computed provided the equation of a state is known. But unfortunately, this is seldom the case for none of the numerous equations of a state that have been suggested so far represent correctly the experimental results in regard to the behavior of the real gas. We have from kinetic theory the equation of a state for 1 mole of an ideal gas PV is equal to RT. The validity of this equation was put to experimental test by number of workers who conducted extensive study with real gases such as nitrogen, hydrogen, CO2. Notable among such studies are initially work of Reynolds and series of experiments by Andrews and different scientists. Amagat made an exhaustive study of the behavior of many gases under different conditions of temperature and pressure. Andrews' experiment on carbon dioxide are particularly remarkable in that they lead to the very useful equation of a state, the van der Waals equation. So, my friend, what is isotherm and deviations from ideal behavior, ideal gas equation? You know the relations between pressure and volume at a particular temperature is called as isotherm or isothermal. If PV is equal to RT is valid, then at a given temperature PV is equal to constant and the isotherm would be rectangular hyperbola. Rectangular hyperbola. But the experimental results with real gases when plotted in a PV diagram gave a completely different picture. In the diagram, you can see 4.1, we have shown the isotherm at low temperature and 4.1b, those at higher pressure. But note that this diagram are not PV diagram, but are plot of PV against P at a given temperature. If PV is equal to RT, where valid PV should be have been constant at a given temperature, whatever the pressure, and the result would have been a straight line parallel to the p-axis. But what do we really obtain with real gases? The finding are, look at this picture. This is for ideal behavior, but no gas on this line. For hydrogen, the curves are positively inclined to the p-axis, showing that the product PV increase with increase of pressure. For nitrogen and carbon dioxide, PV initially decrease with P and then increase with the increase of P. Sorry. The effect is more pronounced in carbon dioxide and less so in nitrogen. Thus, all real gases behave differently from what was predicted by the ideal gas equation. We shall describe the important experiments of Andrews and those of Amang in subsequent section. So look at here the experiments on carbon dioxide. In an attempt to liquefy some of the so-called permanent gases, and important contemporary problems, and Reeves carried out exhaustive experiments on the isotherm of carbon dioxide. So, we shall not enter into the details description of these experiments, but we need some information for conclusions. So, a series of values for pressure and volume of carbon dioxide at a fixed temperature was obtained, and it was repeated at other temperature to get the family of isotherm you can see in this picture, in this figure. Consider the isotherm of temperature 13.1 degrees Celsius. The carbon dioxide is in the gaseous state at A. Look at here, this is the A. And as the pressure is increased, the volume decreases considerably until at B. This is the B point, which corresponds to a pressure of about 50 atmosphere. The gas begins to liquefy. As long as liquefactions continue, the pressure remains constant and volume continuously decreases until all the gas is liquefied. Point C, you can see. The liquefaction process is indicated by the horizontal line BC, where the liquid and gaseous phases coexist. Further, increase in pressure causes only a slight decrease in volume of carbon dioxide, which is now in the liquid state. This corresponding to the steep part CD, you can see here, this CD steep part of curve, and shows that liquids are highly incompressible. So at high temperature, the isotherm have the same general form, but pressure to produce liquefactions increases, and the horizontal portions become shorter, that is the specific volume occupied by 1 gram of substance of vapor at onset of the condensations is relatively smaller, while that of liquid on completion of condensation is relatively greater. So my friend, at the temperature is further raised by 21.5 degrees Celsius. Look at this. The above changes process is the same directions until at 31.4 degrees. The horizontal portion of the curve just disappear and the two volume becomes identical. This is called the critical isotherm for carbon dioxide. Now, above this temperature, the horizontal part of is absent. This one you can see. Absent from all isotherm, and liquid carbon dioxide cannot be produced by pressure volume. And this experiment thus demonstrate that it is not possible to produce liquid carbon dioxide at temperature higher than 31.4 degrees Celsius. And what is called the critical temperature, the pressure just required for liquefaction at this temperature is called liquid pressure, critical pressure, and the volume occupied by 1 mole of substance at this pressure and temperature is known as the critical volume. So the critical isotherm divides the whole diagram into two different regions. Above this, no liquid state is possible even under greatest pressure. The term gas is used for substance above its critical temperature and term vapor for the same substance. So my friends, below the critical temperature, you can see in figure point within dotted line CC P BB BB prime. CC is MBB prime correspond to the coexistence of both liquid and gaseous state in the container with a meniscus separated the two phases. To the left of this area is the liquid region, while to its right is the gaseous region. Now, if change in pressure, volume, and temperature, that takes the substance from A, which correspond to the gaseous state, to D, which represent the liquid state, without passing through the dotted area, then at two stage, any heterogeneity or meniscus appears in the whole mass. For instance, we may heat the substance above 31.4 degrees Celsius, and then compress it till the volume become equal to that of the liquid at that temperature. So next cool add it to 21.5 degrees Celsius and reduce the pressure. This result is stated by saying that 3 existence a continuity of liquid and gaseous state. This is the continuity. So my friend, the conclusions from this experiment: the existence of a critical temperature for all gases above which no gas could be liquefied by pressure alone, a fact of paramount importance in liquefaction of gas. Their existence a continuity of the liquid and gaseous state of substance in spite of apparent discontinuous nature of is isothermal below the critical temperature. And this experiment also formed the basis of an important equation of a state proposed by van der Waals, which holds fairly well in equilibrium. The vapor regions near the above the critical points. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching. And please go through this critical constant of gas definition, what is critical temperature, what is critical pressure, and critical volume.